So let's begin our review of the thermodynamics behind the dancing gummy bear demonstration. The purpose of this lecture is essentially review the most important concepts of thermodynamics for AP biology. However, these concepts, of course, are followed by all things in the universe in terms of energy changes. So they work for any course that you're learning because they're universal throughout the universe. So let's begin our discussion of free energy entropy and the dancing gummy demonstration. So what we have is we have a test tube. As you remember, in that test tube, we had potassium chlorate, and this was a solid, and here is the chemical formula of potassium chlorate. It's a solid, and the first thing we wanted to do is we wanted to melt it. Okay, we wanted to make it into a liquid. And this, my friends, is a chemical change because we're not changing the chemical formula. Notice we have potassium chlorine and oxygen of a particular ratio called the chemical formula, and we have that same ratio here. So it's a chemical change because the chemical formula doesn't change. It's the same ratio of different elements. Okay, and that's why it's a physical change. A solid is becoming a liquid. We're not making anything new here. It's the same chemical, potassium chlorate as a solid, potassium chlorate as a liquid. So in order to do that, okay, I use a torch, and I'm just using this as a flame here. So this flame from the torch, okay, and it was a blue flame, but you get the idea. Okay, this flame melted. Now this flame represents free energy that was released by the reaction of the propane, and that free energy helped melt this reaction. This is a great example of coupling because I have a separate reaction that was exergonic, it exiting out free energy out of the torch. You can actually, visualize that. And it was driving a reaction that's not spontaneous. Now you say, well, how do I know it's not spontaneous? Well, very quickly, you should know that the melting of the potassium chlorate was not spontaneous because it didn't melt in front of you, right? It was sitting there solid, and it would sit there solid forever. It doesn't, at 20 degrees Celsius, it was non-spontaneous. It didn't react. Okay, non-spontaneous means that it was never going to have a pathway to react unless we forced it to happen, and we were forcing it with the spontaneous process of burning the propane. So this is coupling. A exergonic reaction was making an endergonic reaction. All right, but let's focus on just this process here. So melting of the solid, okay, it wasn't happening without the energy, so it was non-spontaneous. But another way to look at it is if you look at the free energy, that free energy is in the reactant side. What does that mean? That means not only do we need potassium chlorate, we needed the free energy to make this product. In fact, we can plot that change here. And I know we're going to start, well, I don't know how to start. Do I start high? Do I start low? But look, free energy is being added to this. So if I'm adding free or giving you free something or giving you something, you know at the end you're going to have more than the beginning. And that's what we have here. We have the free energy we call delta G. Okay, it's called Gibbs free energy. All right, and we know that we have the free energy of the products. So this is the reactants right here, and this is the product. And essentially we are doing what? We are going up. Why are we going up? Because energy had to be what? Absorbed here. Free energy was in the reactant side. So delta G in this process, the change of G, okay, clearly is positive. So if you were given delta G as positive, that would tell you that, hey, we are forcing this to become a higher in energy because we're taking in free energy and we're forcing this to happen. And so therefore it's non-spontaneous because of a positive for going up in free energy. Things in nature, come on, don't go from low energy to high. Things in nature go from high energy. What is entropy? Entropy is the measure of dispersion of energy. We have a concentrated source of energy, and it's going to become a less concentrated source of energy. Hot water becomes cold water at room temperature, or at least room temperature water. So hot water in a room that has a temperature much lower than its own temperature is going to eventually match that temperature, and it's going to disperse its heat, and the room temperature is going to absorb that heat. And so things in nature go from a high source of free energy to a low source. We're going the opposite here. Well, how did that occur? Because we're forcing energy. Great example is, okay, I'm riding a pony. The pony is taking me somewhere. That's free energy. I don't have to apply any energy to walk. But if I break the pony or the pony gets tired, I have got to carry the pony home. If I've got to carry the pony, I'm going to force that pony home, and I have to put energy into a system. So knowing that the energy is going in, free energy, is telling me that this is an endergonic process, that I am actually creating a concentrated source. I'm not going from a concentrated source of energy. I'm going this way. Okay? And that's important when we look at it that way. Now, that's the overall process, but I want us to think about this a little bit differently. Okay? I'm going to add a little layer to this now. Now, when I said the entropy, okay, we talk about this entropy here. We always talk about the delta S of the universe. This is important, the delta S of the universe. Now, if we know that delta G is positive, which means that we're going from a low source of energy to a more concentrated source, which again is going against what the universe allows. The second law of thermodynamics states that always pathways are allowed when you go from a concentrated source of energy. Hey, the energy in the universe is being distributed, right? Isn't the concentrated sources of stars, okay, distributing their energy outward? Of course, it doesn't go the other way, okay? Now, the thing is, we're always measuring this universe. Now, when we look at the entropy, we know that the entropy, okay, has to be decreasing because it's endergonic. We know it's endergonic because it's a positive delta G. I knew that because the free energy was in the reactant side. And notice I said it's non-spontaneous at 20. That's a condition. If this was at 100, if the room was at 100 degrees Celsius, it would already be a liquid, right? So it has to be at room temperature. So this is the trickiest part right here, because I've been teaching you, hey, look at the particles. So I taught you in class that the universe, think of the universe as a big box. Okay, it's a pretty big box. And think of the system is where what we're doing the Gummy Bear demonstration. There's plenty of systems in the universe. Here's the one system. This is the one room that I was doing the demonstration. Okay, so this is the system. Now, when you think with me, this right here is the whole universe. So when we consider the delta S of the universe, we have to consider what two things? We have to consider the delta S, the change of entropy of the system. Okay, that's of course in the box, in this little box, and then we have to consider the delta S of the surroundings, right? That's important, and that collectively will give me the delta S of the universe. Just stay with me for a second because it gets a little confusing. Okay, now we know that the answer is going to be a decrease in entropy because it has to be if it's non-spontaneous. There's no pathway for this to occur. And again, you say, well, how do I know? Because it wasn't melted in front of your eyes without the what? Without the torch, it wasn't melting. It only melted when I kept the torch on, a constant supply of energy to make this go up. It should be logical to you. But what's confusing is you look at this. I've got a solid here, okay? And let me get rid of some of this. I've got a solid here. Now a solid is becoming a liquid. Now when you think with me for a second, solids, okay, are made in crystal patterns. This formula is in some kind of crystal arrangement, packed pretty tightly, and these individual dots represent these formulas. All they're doing is vibrating in fixed positions. They can't really disperse. Now when they become a liquid over here, and I'll get rid of this here, when they become a liquid, okay, then they're free of that crystal lattice. They're able to move more independently. Hello, the degrees of freedom have increased. When I say the degrees of freedom, I'm saying the molecules now have a greater way to move around. And you can clearly see going from a solid to a liquid that the energy is dispersed. Okay, so the system's entropy is always going to be the particles. And so, my friends, the entropy of the system is definitely increasing. Oh, that's confusing. I know, because we said the entropy is decreasing because it's non-spontaneous, but we're talking about the entire universe. I'm breaking the universe down into the two systems. So there is an increase of entropy due to the particles becoming freer as a liquid. That should make sense to you. Now, there's another component here. This energy is being absorbed. Okay, and I'll draw this right here. So this energy is coming from the surroundings, free energy, and of course it was coming from the torch right here. Now, This energy, or free energy, I said, was coming from the surroundings. Now, if I didn't have a test tube here, this torch's energy would make the gases in place of the torch all go faster. Now, of course, it definitely made the gases that were around the torch go faster, but a lot of the energy was taken into the test tube. So there's definitely a transfer of energy into the test tube. That energy, if the test tube wasn't there, would have been used to move more gas molecules. So having this test tube here took in the free energy that could have been using to do what? Increase the motion and dispersion of energy of the gases in the surrounding. So by having the test tube take in the energy, there was a lot less motion that resulted. So the delta S of the surrounding decreased a lot because a lot of the energy went into the tube instead of going into the gas molecules. And so when you compare the surrounding going down a lot, okay, and the delta S of the system going up a little bit, the overall change is of course a lowering of the delta S of the universe. Or you can say it this way, knowing it was non-spontaneous because it's a positive delta G, it being endergonic, it had to be that the surroundings, was much lower, okay, or there was a greater decrease in the surroundings than the increase in the system. The system is always the particles. The surrounding is always due to the heat changes. So there's two components to measuring the delta S of the universe. This is new today. There's the heat exchange. And of course, the degrees of freedom of the particles in the system. We're going to continue that discussion as we go through into the next lecture. Okay, so we're going to move on now. So hopefully we got a good understanding of that. Let's go on to the next reaction. Now, or the next process. So we first did is we melted this non-spontaneous process. Using the free energy of the torch, we coupled and forced this to melt. We kept the test tube on, we kept it on till it melted. And then we kept it on a little longer to make the KCl become free oxygen. That's important. Okay, so let's look at that. Now, so the next part is after I melted the potassium chlorate, I kept heating it until I had this what we call chemical change. And it's a chemical change because what happens is the products have new chemical formulas because there's a new arrangement. Atoms or bonds were broken and disassembled and rearranged here. So chemical changes are when you have new chemical formulas or new chemicals result. Okay, in the last one it was a physical change because we didn't have new chemicals. But in any case, okay, let's think about this. So we kept heating till it became KCl solid, which was basically a white compound, and we had the bubbling of the O2. That is the O2 that I used for the next reaction. Okay, we drop the Gummy Bear that has this disaccharide here, which is a carbohydrate, a sugar. Okay, so let's talk about this. Well, where's the free energy? The free energy is in the reactant side, just like the other process. What does that mean? Well, I had the torch on it. We melted it, but I kept the torch on it to make sure that I was making the liquid become O2. It didn't occur, it was not going to occur unless I kept the torch on. How do I know that? Well, the reaction with the free energy written there, by me putting free energy in the reaction, I'm screaming at you that we needed to keep a constant source of energy on this liquid to make this happen. So if I plot this again, we have delta G. Okay, if I need energy and putting energy into my system, then we're going to start low and then we're going to finish high for free energy. All right, we're going to go up. And therefore, the change of G is positive here. It's going up. Why is it going up? I have a constant source of energy. And think with me, I'm dealing with a low source of energy, and I'm making a concentrated source of energy. That goes against the second law of thermodynamics. There is no real pathway. The universe doesn't allow you to have a pathway that's easily accessible to make a concentrated source. Hey, photosynthesis doesn't work spontaneously. We have to constantly use the sun to keep it going. Well, in this case, I constantly use the torch, okay? So that my products had more free energy in them than what I started with the KClO3. It's important you see that. And we went up because we absorbed. So this is screaming to you that this is endergonic because we're absorbing free energy. You can see that with the written. This is definitely non-spontaneous because it was not going to happen until I keep adding the heat from the torch. Take the torch away, it doesn't work. Take the light away, photosynthesis does not work. Okay, knowing all of that, clearly we know that the entropy is decreasing because we're going from a system of low free energy to high free energy. We're creating a concentrated source here, okay? And so it's a decrease of entropy. But that is problematic because there's two components here. Let's look at those two components, okay? Don't forget, let's draw that box again, okay? And this represents the what? Entire universe, okay? This represents my system. This is where the reaction is occurring. Now, if you look at the what's going on here, we have two of these particles becoming how many? Two of these and three of these. Whoa, two particles are becoming five. What's happening to the degree of freedom? I have two particles that are liquids, and then we make three particles that are gases. So out of the five particles, three are gases. Gases have more motion than liquids. Liquids have to stay in a container. Gases can fly out of them. So for two reasons. Number one, we're increasing the degrees of freedom. We have more molecules who can independently move. And three out of the five can fly away. Clearly, the delta S of the system, okay, is what? Increasing because of what's happening with the particles. So you may say, whoa, Mr. Grotsky, you're saying a decrease in entropy. Well, I'm saying there's a decrease in the universe's entropy. But if there's a system increasing, the delta S of the what? Surroundings has to be a big enough decrease to make the overall universe drop. And what's the big elephant in the room? There's this huge free energy that's doing what? Going from the surroundings into the system. Now you say, well, it's the propane torch. Correct. But just like before, if I didn't have the test tube there to heat this, that heat could have been used to make the surrounding gases go faster. So all that heat that's being absorbed by the test tube is not making the surroundings dissipating and spread out. So we would say that delta S of the surroundings is decreasing a lot because of that. And that's enough to make the overall delta S of the universe to drop for the same reasoning. Bottom line is a positive delta G, okay, means that you're going up because the absorbing energy makes it endergonic. And your entropy of your universe, okay, has to decrease if you're concentrating your products, okay? All right, so the third part of this demo is that the oxygen I was producing by heating the liquid was in this test tube, and I had a lot of it. And then what I did is I added the gummy bear that had this, okay, had the fructose in it. That's what this is, okay, and had the sugars, okay, the disaccharide. And if you remembered, when I dropped, as soon as I dropped this into the hot liquid that had a lot of oxygen, this was a fantastically spontaneous reaction. It gave off light, sound. The gummy bears were moving, and heat and smoke was given off. There was tremendous amount of free energy that was released. And if you noticed, did I have the torch on the tube to make this go? No. This compound reacting with the oxygen in the liquid was spontaneous. You saw it happen without me adding any constant supply of energy. And therefore, because energy was released, it was exergonic. And it's because it's spontaneous, there was a pathway for it to occur, which means the delta S of the universe, okay, was increasing or positive, okay? But, you know, I want to get into the details. Let's look at the what? The total what? Change of entropy of the system here. We have one big particle, so we have one, Now this is 35 over 2 for balancing reasons. So this is like 17.5 particles. There's a reason for that, but let's just round it off to 18 particles. And this is 1 particle. So we have a total of what? About 19 particles over here, right? And then we have what? 12 particles and 11. We've got, if you think with me, 23 particles. So we're going from 19 particles to 23. Hey, the individual degrees of freedom are increasing. So if I draw my box again, okay, in my system right here, the delta S of the system is what? Definitely increasing. We're having more degrees of freedom. Now I don't have this here, but the CO2 is a gas and the water's a gas. This guy's a solid. So if you think with me, this big solid became a lot of gas particles. Okay, so for that reason, there's a tremendous increase in entropy when you think about just the particles. Now, what's different here is that we're releasing tremendous amount of energy. At the same time, I'm releasing this tremendous energy. And what does that energy do? It makes the surrounding molecules do what? Go faster and disperse. So that means the delta S of the surrounding was also going up. And so was the system. The delta S of the system is going up, like we just said, because we had more degrees of freedom, more particles being produced in some of those gases. You add these together and you're going to get an increase in overall entropy. Okay, so don't get confused about always looking at the individual particles. It's one component. Okay, and we're going to get to that a little bit in the next lecture. Okay, so in any case, I'm going to get rid of this, and we want to plot these changes, because one of your skills for your form that you're going to do this weekend is to plot the changes that occur in an energy diagram that uses free energy. And this is new. It's not very hard. Okay, so let's start. Okay, and we always start with the free energy of what you start with and what you're going to get. Because I know that this is spontaneous, because free energy is being released, hey, arrows going out for free energy. If energy is being released, then my product should have less free energy than my reactants. So we start high and we go low. And I'm being OCD here, and I don't like how that line is kind of going up, but I'm going to do my best to draw a straight line. I don't know if it's any better. But in any case, what does this represent? Well, this is C12, H22, O11. That's the energy of that fructose, and, well, probably, it might be sucrose, okay? Who cares? Plus all the oxygens. So collectively, what this represents right here, I'm going to draw another terrible arrow, but this arrow here, this distance from here to here, represents the free energy that the reactants have. That's what that is. So we're going to label this 1, 2, 3, 4, 5, and 6. So the free energy of the reactants, we call this 4. So number 4 is the free energy. This is the total amount of free energy that the reactants have. Well, this makes sense. Carbohydrates have tremendous energy because photosynthesis used energy to do what? Stuff energy into the products. It was a non-spontaneous process. You stop the light, you stop the photosynthesis. So we're starting with a compound that has tremendous amount of energy. Hello, that's why we take in sugars and carbohydrates, because we need energy to do what is, guess what? Endergonic in building things. Okay, now, so that's the energy here. So what is the free energy of the products? Well, who are your products? Your products are CO2, remember they're on the right side of the arrow, and H2O. And collectively, drawing my arrow from the bottom, this is how much free energy they have. It's a lot less. Why? Because a lot of the energy that this had was released as free energy here. That's why we call it exergonic. It's exiting. Okay, that means that your products are going lower. This is logical, people. You have to make it logical. Okay, now, so this is number 5. This is the value for the free energy. Okay, let's do the delta G. The difference of where you start and finish is the change. You guys did slope, change of y, change of x. So we're going to do the change here. So this line right here, from the difference of where we start and finish, and don't make fun of my squiggly lines here, this is number 1. And by the way, aren't we starting high and going low? That's why the delta G is negative. Or we're starting here and we're dropping down to this part right here. That's why delta G is negative. Always for spontaneous processes. Okay? So that's this distance right here is also number 1. Okay? All right. Now I've got to add some things. Number 1, is this a catabolic or anabolic process? I'm taking a sugar and I'm breaking it down into components. You should understand that that's catabolic. Okay? And when we break stuff down, we normally get the energy, and that energy that's released is used to build things in our cells. That's our what? That's our coupling. Okay, I'm going to add some things to this now. This is brand new. Okay, now there's an energy pathway. This is what happens before and after. This is called a state function. This is before and after the reaction, without considering the pathway. All right. Now this is called the reaction pathway, and it looks like this. And it always has a little bump that goes at the top. This little bump here represents a barrier, a reaction barrier. Let me explain. This reaction wants to get to this position here. Okay? If there wasn't this little bump here, this would go directly here, and sugar would always what? Burn right away. But it doesn't do that. So it doesn't react. Remember, all reactions require what? An input of energy. When I burn cellulose, which is made of glucose in the paper, okay, I had to add a spark, or I had to add a what? A lighter to do so. So in order for a reaction to occur, I have to get to the top of the hill. So from here to the top of the hill represents our E of A, which is our activation energy. This represents the energy to start the reaction. And a great analogy is slides. If you love slides like I do, you want to, if you're driving and you see a park, you stop and you ride the slide. I hope you don't. But the point is, to ride a slide, you got to get to the top. Well, in order for this reaction to go, we have to get to the top. So we have to add energy a little bit to get to the top. Even though that this is exergonic, there is a little bit of energy that we have to add to get this to the top part. And remember, to ride a slide, you have to get past the top part, and of course the reaction goes. So this is a reaction barrier. And this line right here from the top peak to where we start is our activation energy. Every reaction requires an input. Every reaction has what we call a reaction barrier. Now, what really is that? I can't just tell you that. In order for reactions to go, we take this sugar and it has to slam into the oxygen molecule. Things react because of collisions. In fact, they only react if that collision is effective. An effective collision is a collision in which the kinetic energy, or the motion of these particles, is enough to make the reaction go. There's a reason why we need this amount of energy. And the outside of atoms and molecules is electrons. Electrons are negative. So there's a cloud of negatively charged particles. Oxygen has them too. Every atom and every molecule has them. So when these guys are going to collide, they're going to repel a little bit because they have that cloud of electrons. So they have to go fast enough to overcome these repulsive forces. That's what activation energy is too. Besides, to be an effective collision, you also have to collide with a proper orientation. There's 2 points. So first part of being an effective collision, you have to have enough kinetic energy to overcome repulsive forces. That is E of A. That is activation energy. And that's why every reaction requires an input of energy. Hey, bombs explode because they have to be inputted. They don't explode by themselves. Okay, they have to have an input of energy. All right, every reaction does. Now, there's a second component that requires have proper orientation. We'll talk about that toward the end of this. So that's what 3 is. Okay. Now, what is the activated complex? Now, the activated complex is this arrow from the bottom all the way, that's a pretty straight arrow, all the way to the top of this peak here, to the top. Okay. And this, of course, is 2. Now, what's the activated complex? The activated complex is the highest energy position that these two molecules have to overcome. So think about it, that these guys are coming in close, 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 and they're just at their peak of their repulsives, and any closer, the reaction will go. So this represents the peak point. Some people think it's the place where the sugar and the O2 are just about bonded, and they call that a complex. The bottom line is it's the maximum position we have to go. And there it is, all right, that we have to overcome. In order to ride the slide, you've got to climb and get to the top. You have to add energy, okay? And that's what the activated complex is, all right? Now, there's one more piece to this as I scroll down. You notice number 6 is the activation energy with an enzyme, okay? Well, my gosh, let's bring this to full circle. We know our DNA codes for what? It codes for amino acids. Amino acids make polypeptides. These are proteins, right? And these proteins, guess what? They fold into a certain shape based on their R group. And so think about this. They have a three-dimensional shape called these active sites. Now these active sites collect substrates. So let's pretend sugar can fit right here. Let's pretend oxygen can fit right here. What the enzyme does, it has these three-dimensional active sites that collects the substrates. This is the sugar, here's the oxygen. And so what it does is it helps the collisions occur at lower energy. See, we know that the collisions have to be effective for the reaction to occur, but they have to hit each other. Think about being in a cell. These things are moving in all directions randomly. What an enzyme does is help them find each other. Think about all the motion that a sugar has to do and an O2 has to do in order to find each other if it was in a cell. And if you don't like that, just think of other substrates that are better in cells. They have to expend a lot of energy to find themselves. But if an enzyme comes around and just moving and collects them, it puts them what? In close proximity so they can what? Collide and collide effectively. Not only that, it actually exposes areas at which they bond more effectively called proper orientation. Remember, in order to collide, you have to have high enough kinetic energy, but you have to be hit in the right way. This is really true of big macromolecules, like sugar. They have to be nailed onto the carbon that's double bonded to the O. They have to be hit in a certain way. So enzymes, what they do by helping collect the substrates, the individual components who want to collide, they kind of help them as matchmakers collide, and they don't have to expend so much energy bouncing around to find each other. So they actually lower this hump. So this pathway I'm drawing is for an enzyme, so I guess I should do it in a different color. So this is a new pathway. You notice it doesn't change. It doesn't change the 4, the free energy of the reactants. It doesn't change the 5, okay, which is the free energy of the product. So therefore, it doesn't change the delta G. But what it does is it lowers the energy barrier. Now, I'm going to draw a new little arrow here. And this arrow is for number 6. This activation energy has been lowered. Why? We need less energy to make these guys collide because they're not going to expend so much energy bouncing around. They're going to collide more often, expending less energy because the enzyme is going to help put them together. That's how it works, people, okay? And that's why we need energy, and that's why we need enzymes, and that's why DNA codes for the polypeptides. They make reactions that are spontaneous, but they make them occur at fast enough speeds that matter and sustain life. That's why we have enzymes. They lower the activation energy so that these things occur more often. You say, well, I don't understand how they occur more often. Well, let's pretend you and I are going to have a race. You are going to climb this bigger slide, and I'm going to climb this smaller slide. And we're going to see who can get more rides in their respective slides in a time period. Well, of course, I am going to win because it takes less effort to climb the slide. Well, think about that. with the same time period, I'm going to have a lot more rides, a lot more chemical reactions occurring with less energy input because my slide height is smaller. My activation energy is smaller. So we're more efficient. We increase the rate. The rate means the speed. We are not, and this is important, this was in your form, we are increasing the speed at which a reaction goes. But are we increasing the delta G? Are we changing the difference of where we start and where we finish? And the answer is no. We are not changing the spontaneity. How spontaneous we are is how negative delta G is. And how negative is how far apart these two lines are, starting high and going low. This just changes the pathway. All right, and that's important. So I go to the last question. What provided the energy to overcome the reaction barrier? Well, it was the hot beaker made from the propane torch. The propane torch, which was a spontaneous process, coupled the reaction. So the free energy of the hot solution provided the energy to overcome the barrier. All right, this is a lot of stuff that I hopefully we connected together, but there's one more thing that I want to do here, and I want to take a look at quickly a picture of this process. Okay, so we're just going to look at the gummy bear demonstration just in the terms of using the torch to melt it. I know there's a chemical reaction here, but let's look at this. Okay, the first part we're going to look at is we had propane torch. That's the propane right there. And there's the oxygen on the outside, and of course there's our propane torch. So it was a spontaneous reaction. Well, why? Well, it gave off free energy. It's exergonic, right? Exergonic right there. Okay, now, what else? Well, I know that delta S of the universe is increasing. I have 6 particles here, okay, becoming 7. And this is a liquid, and some of these, and all of these are what? Gases. So you know that the what? The delta S of the system's entropy is increasing, and because I'm releasing heat to the surroundings and making the gases go faster, the delta S of the surroundings increasing, so the delta S of the universe is increasing, so therefore it is spontaneous. But any case, you notice there was no reaction making the propane torch go. There's no torch for the torch, okay? Now the heat, the energy, the free energy released drove this second reaction. Remember, this test tube didn't what? It didn't melt until I kept adding heat, and I had to keep the torch there to melt it because I needed a constant supply of energy because I had to climb, okay? So I had to climb that hill. So this was non-spontaneous because energy had to go into the process. That's why this is going up and delta G is positive, okay? We were creating a concentrated energy source. Here, I was using a concentrated energy source to release the energy. This was exergonic. Delta G is going down. Notice the pathways here, okay? Now, we weren't using any enzymes, but this was giving off energy that we were using. This is coupling. But I want to talk about what we talked about today. All the free energy I released was not going into this system, right? Some of it has to escape into the surroundings. Every exchange of energy from one system to the other, you have to lose some. Why? By losing some, you're dispersing the energy. Energy has to be dispersed. You can't convert one energy directly into the other. You would break the second law of thermodynamics. So we use an exergonic process to drive an endergonic. We used a spontaneous process to drive a non-spontaneous process. This is what happens in biology. We break down food that gives off the energy. We use that energy to build a non-spontaneous process. Most things cells do are non-spontaneous. We make proteins. We put amino acids together. We put sugars together to make starches, okay? We make proteins, okay? We make nucleic acids, more DNA. We make more cells. There's a tremendous amount of concentration in living. As I said in class today, the reason why fossil fuels have so much energy because living things collect energy. Living things use other energy to collect more energy, concentrate. But there's always what? A loss of energy in the process. Has to be, because the delta S of any change, any process, has to be a loss of dispersion of energy. So some of the heat in our transfer has to disperse for this to work. A pathway exists when what? Energy is dispersed, or some of that energy can what? Go and become disordered. So some of that energy, and sometimes a lot of it, has to leave. And that's where we lose the free energy, just like the Vsauce video says. Okay? We're losing free energy. Energy is not, there's no such thing as a renewable resource here. Okay? Because once we use a free energy, it's gone forever. So the free energy in the universe is decreasing over time. And it's going to decrease to a point where the same free energy is everywhere in the universe. And these graphs will be straight lines. And that'll be what? Equilibrium. And that'll be the death of all processes, because nothing can occur. Everything that occurs in nature, every change requires, okay, a change of energy and a release of energy. Therefore, free energy gets dispersed. So important, you can see this. But look at this right here. This reaction released 2100 kilojoules of heat. Don't worry about kJ, it's a unit of heat. This one accepted 1000. Why is there a difference? Remember, it's minus, I'm releasing it, this accepted. The difference is what's lost forever. Lost forever. For this process to work, some of this free energy had to be released forever. And that means it's dispersed, it's no longer concentrated. Okay, we're making some concentrated, but we can't convert all the free energy into a concentrated source. There's no perpetual energy machine. A lot of it has to be lost there. That's really important. So the exergonic process drives the endergonic. And this is what we do in our bodies. We use foods catabolically, break them down for energy, to anabolically do the things that cells do. And I hope you can see that a little bit better in this process. All right, so I hope that helped. All right, and we'll finish this now. So again, the energy released going down is the same energy that was needed to be absorbed, but they couldn't absorb all of it. And that loss of energy is what makes the universe's, again, free energy go down. And of course, back to the video, the Vsauce video for the last little point, what kind of life are you leading? Are you adding to the loss of free energy, which by the way is going to lead to the death of the universe? When all the concentrated sources of energy are used up and everybody has equal amounts of energy, then everything stops in the universe. Things don't change unless there's a change of energy or transfer of energy. You can't have it if everybody has the same amount of free energy, and that's equilibrium. So what are you doing? If you work hard, you're using up more of the free energy and leading to the universe's death faster. If you're lazy, you're using up less of the energy and you're keeping it longer for other people like us to work hard. So I hope you saw that in the video and found that interesting. Okay, good luck with this.